The first vending machine. The Romans didn't invent the vending machine to sell food or drink. They built it to stop people stealing from a temple. Drop in a bronze coin, and a measured splash of holy water pours into your waiting hands. No priest, no attendant, nobody watching to make sure you take only your share. Just a machine that takes your money and hands back the product, running in the 1st century AD, nearly 1900 years before the one humming in your office hallway. And the vending machine is the least impressive thing they built. The engineer behind it left a book explaining exactly how it ran. His name was Hero of Alexandria. Egypt had been a Roman province since 30 BC, so Hero was a subject of the empire, and the device sits in his treatise on pneumatics, written in the 1st century AD. The mechanism is almost insultingly simple. A coin drops through the slot onto one end of a small balanced lever. Its weight tips the lever, which lifts a plug off a valve and lets water flow, until the coin slides off the end and the valve drops shut. One coin, one measured pour. Hero was solving the oldest problem in any temple. Worshippers kept taking more holy water than they paid for, so he built a machine that rationed it and pocketed the coin. Strip away the temple and the togas, and you have the exact logic inside every coin-operated machine since. We did not invent that idea. We just plugged it into the wall. Handing someone an exact measure of water was one kind of clever. Using water to measure something you cannot hold at all was another. The Romans did that too. They used it to keep time. The water clock. For most of human history, a water clock was just a leaking bucket. Water dripped from a vessel at a supposedly steady rate, and you read the time off the falling level. The trouble is the rate is not steady. A full vessel pushes water out harder than a nearly empty one, so the first hour of the day ran short and the last one dragged. Around 270 BC, a Greek engineer in Alexandria named Ctesibius fixed the flaw everyone before him had simply lived with. His answer was a second chamber that kept the water feeding the clock permanently topped up, so the pressure never changed and the drip stayed even. Ctesibius is often called the father of pneumatics. He worked in Alexandria more than 2 centuries before Rome ever took Egypt, but the Romans inherited his improved clepsydra and put it to the most Roman use imaginable. They installed it in their courtrooms. Each speaker got a fixed ration of water, and when it ran dry, you stopped talking, finished or not. It was the original way to tell a lawyer his time was up. Ctesibius had learned to make water and air do precise work on a schedule. About a century later, another man in that same city, Hero of Alexandria, used those same forces to build the strangest machine of the ancient world. It opened nothing, lifted nothing, carried nothing. It just spun. The Aeolipile. The Aeolipile was a steam engine, built 16 centuries before anyone got around to putting one to work. Hero mounted a sealed bronze sphere over a boiler, with 2 bent nozzles sticking out of opposite sides. When the water beneath it boiled, steam rushed up into the sphere and jetted out through the nozzles, and the recoil spun the ball fast enough to blur. It is the same reaction that throws a rocket off the launch pad, running in a workshop in the 1st century AD. And the Romans did absolutely nothing with it. There was no drivetrain, no gears, no attempt to hook the spinning sphere to a mill or a pump or a wheel. It impressed visitors and then went back on the shelf. A steam engine that did real work would not arrive until Thomas Newcomen built his mine pump in 1712, and the Industrial Revolution grew out of that. It is tempting to call this the greatest missed opportunity in history, but that is mostly hindsight. Steam only pays off when labor is expensive, and your metalworking is good enough to hold high pressure without bursting. Rome had cheap labor in every direction, and metallurgy that was nowhere near ready. The machine was real. The reasons to build a bigger one were not there yet, so the Romans had the first spark of the steam age turning on a bench, and walked away from it. The mechanical genius they did take seriously. They pointed at people. They wanted to know how to kill a man standing 400 meters away. Torsion Artillery. The Scorpio could put a bolt through a man at 400 meters, and it did it without a bow. The power came from twisted rope. 2 thick skeins of sinew or hair, wound impossibly tight, stored so much energy that when the arm snapped forward, the bolt left faster than the eye could follow. This is torsion artillery, and it was the most precise killing machine in the ancient world. The Scorpio was the sniper of the family, a bolt shooter accurate enough to pick off individual men, lethal at around 100 meters on a flat shot and able to lob a bolt past 400, firing 3 or 4 rounds a minute in trained hands. Vitruvius wrote down how to build them in the 1st century BC. 400 years later, the officer and historian Ammianus Marcellinus described them still tearing through battle lines. A A single Roman legion went to war with somewhere around 55 to 60 of these machines, and Caesar's troops leaned on them so heavily in Gaul that the bolts became a psychological weapon as much as a physical one. The bigger cousins scaled the trick up. The ballista hurled stones of around 27 kilograms. The late Empire onager, nicknamed the Wild Ass for the brutal kick of its recoil, threw rocks of up to 80 kilograms, hard enough to break a wall, and shook itself half to pieces doing it. There was one thing all this twisted rope could not beat: weather. The skeins were organic fiber, and damp fiber goes slack. A long rainstorm could drain an entire artillery park and leave a battery of precision weapons as expensive furniture until everything dried. And the best skeins of all were made from human hair, prized for its springiness, a detail that sits behind one of the grimmer footnotes in ancient siege warfare. Cities under attack cutting off women's hair by the basketful to keep the machines fed. The same civilization that engineered better ways to end a life put just as much genius into supplying a city with water. The proof ran for kilometers before it reached a single home, downhill the whole way, by margins too small to see. The aqueducts. The aqueducts didn't move water with pumps or pressure. They ran it downhill on a slope your eye can't even see. The aqueduct that supplied the city of Nims fell about 17 meters across roughly 50 kilometers of channel, and on one stretch, the engineers held the drop to roughly 7 millimeters per 100 meters, surveyed by hand with water troughs and hanging weights. Across valleys and hillsides, they had to bridge and tunnel to cross. Rome had been doing this since 312 BC, when censor Appius Claudius Caecus built the first aqueduct, the Aqua Appia. In the same year, he started the famous road that still carries his name. By the time the water commissioner Fontinus wrote his report in 97 AD, 9 aqueducts were pouring into the city, where the Nîmes Channel had to cross a river gorge. The Romans threw up the Pondugia, a bridge of stacked stone arches standing nearly 49 meters tall, the highest aqueduct bridge they ever built, and still standing in the south of France today. The impressive part is the precision, not the scale. Holding a gravity gradient that fine over that distance, with nothing but the chorbates that Vitruvius describes as a handful of plumb lines, is a feat a modern surveyor with a laser would quietly respect. It was a level of engineering Europe would not reach again. Reliable running water on the scale did not return until the 19th century. Every bit of that was about moving water gently, exactly where they wanted it and nowhere else. The Romans also worked out how to do the violent opposite. They could turn that same water loose on a mountain and wash the mountain away. Las Médulas. At Las Médulas in northwest Spain, the Romans mined gold by destroying the mountains that held it, not tunneling for it, destroying them. They call the method ruina montium, the wrecking of mountains, and it worked exactly the way it sounds. The whole technique ran on water, moved by the same engineering that fed Roman cities. Crews cut at least 7 aqueducts across the hills, some of them 80 to 100 kilometers long, to gather huge reserves of water above the mine. Below it, they dug dense networks of narrow galleries deep into the rock. Then they sent the stored water crashing into the tunnels all at once. The trap pressure blew the mountain apart from the inside, and the collapse washed the shattered, gold-bearing rock down into sluices where the metal could be sorted out. Pliny the Elder watched it happen as a Roman official in Spain in the 1st century AD and called it a labor that went far beyond the work of giants. He put the workforce at around 60,000 people. What they left behind, a landscape of raw red rock spires standing where a range of hills used to be, is still there today because the ground never fully recovered. Pulling a mountain apart was one way to deal with stone on a massive scale. Putting stone exactly where you wanted it, tons at a time, and dozens of meters up, took something cleverer than brute force. The crane. A Roman crane let one man lift what it took 60 men to lift in Egypt. To raise a 2.5-ton block up a pyramid ramp, the Egyptians needed around 50 workers hauling together, roughly 50 kilograms of lift per person. A Roman with a compound pulley could move 3,000 kilograms on his own. Same muscle, 60 times the result. The secret was gearing the load down through pulleys. The simplest hoist, the trisbastos, ran a rope through 3 pulleys and let one man raise about 150 kilograms. The polybastos added more, so a 4-man crew could lift 3 tons. Replace the hand winch with a giant wooden tread wheel, the magna rota, with men walking inside it like a mill wheel, and that same crew could raise 6,000 kilograms. Vitruvius wrote the designs down in the 1st century BC. For the heaviest work, the Romans built lifting towers powered by teams of capstans on the ground. They used them to raise the stone capital of Trajan's column, a single block of over 50 tons, more than 30 meters into the air. At Baalbek in Lebanon, they set blocks of 60 tons and heavier. The Egyptians moved more stone with more men. The Romans moved it with machines. A crane could raise 60 tons of cut stone into the sky. But the most advanced thing the Romans ever built was not the stone they lifted, quarried, or carved. It was the gray sludge they poured around it. Self-healing concrete. Roman concrete could repair its own cracks, and we only worked out how in 2023. For centuries, scientists saw the little white lumps scattered through it as the sign of sloppy, badly mixed work. A team at MIT led by Admir Masic showed they had it exactly backwards. Those lumps, called lime clasts, came from deliberately mixing the lime while it was still scorching hot, and they work as a built-in repair kit. When a crack opens and water gets in, it reaches a lime clast, reacts, and the dissolved calcium recrystallizes inside the crack and seals it. The concrete heals itself. It will not rebuild a wall that has already fallen, but a hairline crack that would doom a modern slab. Roman concrete can quietly close on its own. The base recipe, opus commentisium, was almost crude. Lime, a volcanic ash called pozzolana, and rubble aggregate. The hot mixing was the whole secret. You can see what that buys you in the Pantheon. Its dome has held itself up over Rome for more than 1900 years with no steel reinforcement inside it, and it is still the largest unreinforced concrete dome on Earth. A modern concrete foundation is expected to last 50 to 100 years before it starts to fail. The Pantheon was finished under the Emperor Hadrian around 126 AD, and it is still carrying its own roof without complaint. Then the empire fell, and the recipe fell with it. Europe could not reliably reproduce concrete this good for more than 1,000 years, and the formula has only recently been pieced back together in a laboratory by people studying a building that had been standing the entire time, waiting for them to catch up. The empire that poured that dome had been gone for 15 centuries. The dome has not noticed.